part of the ASIC system on chip SoC design methodology is the functional verification and the manufacturing test verification. Therefore, my objective is to illustrate the SoC verification paradigm from a conventional verification process and universal verification methodology, UVM. Split transactors. So the objective is to move as much of the UVM test bench code onto the accelerator or the emulator box in order to speed up simulation. This means splitting each transactor, that is the UVM driver or monitor, into two parts: a lightweight proxy or a wrapper that continues to run on the host, and a synthesizable part, which is the BFM or bus functional model, that runs on the box and wiggles the pins of the device under test, the DUT. So in order to accomplish this task, the code has to be structured into two separate domains: an untimed HVL domain that contains the UVM environment or verification environment, and which must not contain any delays or clocks; an HDL domain that instantiates the DUT, the device on the test, and the synthesizable parts of the transactors can be run entirely within the box. The synthesizable test harness contains code to generate the clock and the reset, and the code to instantiate the bus functional models, the BFM. So the pin level interface and the DUT. The untimed test bench instantiates the UVM environment. So it is important to note the untimed test bench is that the virtual interface within the top level configuration object is set to point to the BFM interface within the test harness, that is top underscore HDL underscore th.bus underscore BFM underscore 0. This is a full hierarchical reference to the interface instance of the bus underscore BFM underscore 0 within the top level module. So when the UVM driver and monitor proxies communicate with the code outside the class-based verification environment using local virtual interface variables, they will actually be communicating with the BFM in the synthesizable test harness. The UVM code generator interface template file contains settings to include various user-defined code fragments required to define the UVM driver, such as the proxer or wrapper for the full driver transactor, much of which is implemented on the HDL side in the synthesizable bus functional model, BFM. UVM component test for registers. The UVM does reads and writes to the address map. Then it locates agents with wiggle pins for the design under test, the DUT, and the test can be reused. Connected to the predictor, then to the adapter, and set the sequencer map, and then sets the auto predict 0 to expect exclusive prediction. So the register sequence, class, bus, object, and utilities write and read to the register map, and then checks the status value. Therefore, the register transfer model writes values through R0 in the register in the address map, and reads values to register R1 in the register block of the address map. Then it sends to the adapter the generic read-write address data directly from the address map for protocol-specific read-writes to the sequencer, and it generates transactions and transfers and reads information to the DUT, the device on the test, or the sign on the test. The agent sets information to the predictor and transfers information back from the adapter to the address map registers R0 and R1. The information is also set through the HDL path of register 5 within the DUT device on the test, and the mirror is modified by the predictor within the register block. Register 0 sets values as they are desired, and register 0 also gets values returned as they are desired. As stated before, the register model provides a layer of abstraction, read and write registers, an object instantiated between sequences and scoreboards, and agents that abstracts details of control and status registers in the DUT, permitting sequences and scoreboards to access register by name. Now I will talk about the test plan creation in the universal verification model. The tests are applied to the DUT and fed to the signal generator to generate the input to the bus functional model, that is the BFM, in order to drive it to the DUT device under test. The input monitor collects the status from the BFM, the bus functional model, to the DUT, and the output monitor collects the response out of the DUT, as it is illustrated in the system block diagrams of this presentation. The input packet and the output packet response is fed to the scoreboard and checker, and compares the response from the DUT device under test and the reference model output. The build phase and physical connection of all components are done through the test generator or the test generator and of the packets to the BFM is the most time-consuming of the verification process. And the run phase collects the process from the device under test into the output protocol monitor and calls it in the scoreboard, as you can see from the block diagram, to run the test cases on the device under test. If the test case or the test cases are clean, then you can report the results and get an actual report. Test software script. In this framework, I illustrate the flow of the top-level test methodology in the complete software test scripts, including the build phase, which does the sequencer, driver, monitor, and sets packets, parents, and configuration. Get method, the connect phase, which sets the ports and instantiations, the end of elaboration, and the start of simulation. Then followed within the flow, the run phase, which is the main logic, the SoC system itself, the positive edge clock, followed by extract, check and reports, end of class, and finally the end of task for the device under test, the DUT. Configuration object associated with a component and stored in the configuration database, which is used to configure the behavior or structure of its associated components. A configuration object is constructed and initialized by the module, test, or environment, and is read during the build phase. The configuration database is a repository for storing the configuration information as stated previously, used to parameterize the verification environment. Thus, an important element of the universal verification methodology paradigm. The configuration environment can take place during the build phase of the design methodology. Also, information flows from top down, and it sets parameters on the configuration database. The low-level components get those parameters out of the configuration database, so you can configure anything. The UVM component hierarchy, such as memory depths, file options, anything in the test bench. And you can set a virtual interface. You can get individual components out of the configuration database. The agent retrieves the information within the database. Bus Functional Model, BFM, also known as a Transaction Verification Model, is a non-synthesizable software model of an integrated circuit component having one or more external buses. The emphasis of the model is on simulating system bus transactions prior to building and testing the actual hardware. BFMs, bus functional models, are usually defined as tasks in hardware description language, HDL, and applies stimulus to the design under verification via complex waveforms and protocols. BFM bus functional model offers a two-sided interface. One interface side drives and samples low-level signals according to the bus protocol. On its other side, the tasks of the BFM are available to create and respond to bus transactions. So, therefore, bus functional models are often used as reusable building blocks to create simulation test benches in which the bus interface ports of the design under test, DUT, are connected to the correct BFMs. The test bench presented in this project is a monolithic file, which I break into several files to make it more modular and reusable. In this test bench consists of three modules: the test module, which drives stimuli and/or stimulus; the coverage module, to capture coverage of the DUT, the design under test; the scoreboard module, which checks and compares that the device under test, the DUT, is working correctly. Signals are passed using the pointer and generates and initialize the clocks. The send task used for operation and performs reset on no ops in a negative edge or on a positive edge. It also gets data sent as OOPS. You can see the coverage module at the top. It takes the ALU and at the end of the test bench waits for a negative edge of the bus functional model clock and sends to the coverage block. The scoreboard module of the code waits for the positive edge of the BFM, the bus functional module, and edge finally, and the positive edge finally, it predicts the result as illustrated on the test bench code. So the result is predicted and finalized by the scoreboard module. The test top-level user-defined hierarchy. includes the test object, which is instantiated, and behavior and structure modified to increase functional coverage. Also, the ASIC system on chip SoC UVM does the class UVM sequencer and coordinates and arbitrates all transactions generated by the sequences. This will include constraints from a global and circuit constraint, max area for timing constraints, input arrival time, and power. The system on chip illustrated in this framework consists in the implementation of 8 different IP units. The SoC consists of the APB and AHB slave, the USB, the GPIO, and the PCI and AXI, AHB, and the reset. The device under task consists of all the above, with an AHB master and slave. The test bench and the stimulus for all sequences are also included. The transactions are driven by several UVM sequencers, which drive the SoC stimulus. The ASIC system on chip verification design methodology performs the UVM virtual sequences and device or design on the test, and it also performs a reset of the devices, configures the device, generates different scenarios, and verifies the GPIOs, and drives the register sequences, also drives the reset sequence bus, and uses the APB to drive the stimulus to the GPIO, and each sequence will be driven one by one as it is illustrated in the block diagrams of the test structure verification.